Well, it was pretty stupid, I guess. I mean, I did know better. But I could see that one of the problems was in a motor lead, and it was only a 220 motor, and the operator was standing right there with me, so I didn't even bother to tag it. I just guess it was too much trouble to walk all the way back and pick up my tags. Anyway, I was leaning in across the machine and touching me right here, and I reached over and grabbed one of the motor leads, and when I did, somebody, I'm not even sure who, threw the breaker, and I took a real jolt right up my left arm and down out through my heart, and didn't even know what happened really at the time. And I was really lucky, though. There was somebody there who could save me. He pulled me off the machine and got my heart going again. And then next thing I knew, I was in the hospital and just never did even find out.
Yes, he was lucky. People do die on low-voltage circuits. Today's program is about electrical safety, especially safety around low voltages. Many of the points we'll cover apply to all electrical circuits, but we're not going to deal with the special precautions necessary in high-voltage work. Instead, we're going to concentrate on those everyday encounters that electricians, operators, and other maintenance personnel have with electricity below 600 volts. Now, I know that some of you out there feel pretty comfortable around these voltages. But if that means you're not paying close attention to good safety practices, well, believe me, that can be a big mistake. Every year, there are over 1,000 people killed by electricity in the United States. And over 1/2 of these electrocutions involve low-voltage circuits. And did you know that people have been electrocuted by voltages as low as 50 volts? That's right. Under certain conditions, 50 volts can kill. And in a few minutes, you'll understand why. Now, there are quite a few ways to think about electricity, or to explain how it works. But when what you're worried about is safety, this is a darn good one. Electricity is energy looking for some place to go. And when it finds the path of least resistance, whether that's through a light bulb, a motor, or a human being, it's going to take that path. Until a circuit is completed, electricity is in a form we call potential energy. It's waiting to be used. But no current will actually flow until a complete path is created, which is what happens when you throw a switch, say to a motor. This is the path that we want the current to take. It's the safe path, the useful path, and we do everything we can to keep it there, like put insulation around wires that carry the current. Now, if you should become a part of the circuit, like the motor, the current would flow through you, and many people do get injured or killed in this way. But most low-voltage mishaps occur another way. Now, you may have heard the phrase, electricity flows to ground. What this really means is that electricity flows through the earth very readily and can use the earth to complete a circuit. Now, if you are in contact with the ground through a good conductor, say you're touching a piece of metal, like a grounded machine casing or part of a building's plumbing system, or even in some cases making good contact with a concrete floor, and you also come into contact with a live electrical source, you can easily become the path the current will take to ground. This is what happened to the electrician we interviewed at the beginning of this program, and he was nearly killed. You don't want to become a part of this kind of circuit either. How badly you might be hurt depends upon three things: how much current passes through your body, for how long a time you are in contact with it, and whether it passes through a vital organ, especially your heart. If it does pass through your heart, the current from a 110-volt circuit, ordinary house current, could kill you in a small fraction of a second. Now, very shortly, we're going to get into some very practical ways to avoid injury from electrical current. But first, I want to be absolutely certain that you understand why low voltages can present a hazard. I want you to know why this broken lamp housing, or even this open 110-volt receptacle, could kill you. This formula may look familiar. It's called Ohm's law, and it states that the amount of current flowing in a circuit, which is measured in amperes, is equal to the voltage divided by the resistance of the circuit. Resistance is measured in ohms. Let's use this formula for a moment to find out some things about the circuit we looked at a moment ago, the one you want to avoid. Experts disagree about how much resistance human skin offers to electric current under different conditions. But they do agree on one thing. If the skin is wet, say from perspiration, or if there is a cut or break in the skin, then the human body will offer a resistance of around 1,000 ohms. Now suppose you were shocked on a 110-volt circuit. How much current can pass through you? The math is easy. 110 volts divided by 1,000 ohms equals 0.11 amps, or 110 milliamps. But it may not be so easy to understand what this really means. It doesn't sound like much current, does it? It's only about 1/10 the current drawn by a 100-watt bulb. Well, remember that number, 110 milliamps. Now, it's hard to pin down the effects of current on the human body. Historically, very few people have volunteered for experiments. But most experts would agree with these figures. At only 15 milliamps, you could experience a sudden muscle contraction. If you're working on a ladder or scaffold, this contraction or the pain of a shock like this could make you fall. It's happened. Or your hand muscles could contract, making you unable to let go of whatever is shocking you. Here, in this range, depending on your age and physical condition, the loss of muscle control becomes an even greater problem. And here, this is where our 110 milliamp shock belongs. Between 100 and 200 milliamps. That's between 1 and 2/10 of an amp. If the current passes through the heart, it can cause fibrillation, which means that your heart's normal rhythm is confused. It's like putting a pacemaker on your heart that's telling it to beat 3,600 times a minute. And once fibrillation occurs, it takes the immediate use of some pretty sophisticated medical equipment to restore your proper heartbeat and prevent death. Now, maybe you're wondering why you didn't die every time you got bit by a 110-volt circuit. Well, if it's not because the current just plain missed your heart, it's because you had some additional insulation from your skin or your shoes. As the resistance you offer to the current increases, the amount of current that passes through your body goes down, which is a darn lucky thing. But remember, too, that as the voltage increases, so does the amount of current that can go through you. Do what the man we interviewed did. Take 220 volts right across your heart when your body is wet from perspiration and offering a resistance of only 1,000 ohms. And you're going to be very sorry. So stay out of the circuit. How do electrical accidents happen? Because of defective equipment? Well, sometimes. But you know what? Equipment doesn't take chances. People take chances. And equipment doesn't think. People are supposed to think. And people are supposed to care enough about their safety and the safety of others to stay alert and follow the rules. The vast majority of electrical accidents could have been avoided. Most of them occurred either because people were unaware of the danger of the situation or because they simply got careless and stopped thinking about their safety. Let's take a closer look now at some of the things they should have known about and respected. It might just save your life or someone else's. First of all, copper or aluminum is rarely used in electrical circuits except to carry current. So whenever you see exposed copper or aluminum, you should regard it as electrically live and treat it accordingly. And the same thing is true of any electrical circuit. Unless you know for certain that it is dead or de-energized, you must assume that it is electrically hot and treat it with respect. If you are working near enough to a live system to be in any danger of becoming part of the circuit, place insulating material safely between you and the point of danger. Some rubber is carbon impregnated and will conduct current, so use an approved insulation. And make certain it is dry and in good shape. Current can snake through even a small crack. If you are working on a live circuit, well, it's generally accepted by industry that it's best not to work on a circuit unless it has been de-energized. And if you absolutely must work on a live circuit, consult your supervisor or follow your plant's established practice very carefully. Now, when you need a circuit de-energized, you must make absolutely sure that it is dead and that no one can mistakenly energize it. You are going to have to perform what's called an electrical lockout. Most plants have very detailed and rigid lockout procedures that must be followed exactly. Locking out a circuit correctly and safely is extremely important to protect yourself and others from injury. Be sure to follow the procedure that has been established at your plant or facility. And if you don't know exactly what it is, you need to find out. One more thing about keeping people safe when you're working. Don't create a hazard. If you've exposed any parts of a circuit that could cause a shock, keep other people away from the area with barriers and warning signs. We pointed out a few minutes ago that when people do get shocked on low voltage, it is usually because they complete a circuit from a hot line to ground. We've set up a demonstration to make the point even more strongly. This 100-watt light bulb represents a human being, maybe you. We've wired it between the hot leg of the 110-volt circuit and the casing of this motor. The motor is plugged into a 3-wire circuit, so its case is well grounded. Now, when we throw this switch, completing the circuit from hot to ground, the bulb lights up brightly. Now, that's far more than enough current flowing to electrocute a human being. What you see here is what happened to the electrician who nearly died. And you don't have to be touching a metal ground. Damp concrete is a good conductor, especially when it contains metal reinforcement. The point is that you are often standing on a very good connection to ground when you are working. So it's a good idea to make sure you haven't picked up a nail or scrap metal that could bring your body into direct electrical contact with the floor. But even more important, stay out of the circuit. Now, sometimes equipment does fail, or people make mistakes while working. This is why a separate ground wire is provided on machinery and tools which are not double insulated. If a short circuit in the equipment causes the case or housing to become electrically live, the ground wire is designed to make sure that enough current flows to trip off the circuit breaker. Maintaining this good pathway to ground is a vital part of electrical safety practices and demands everyone's attention. In the event of trouble, you want that breaker to trip off, and as quickly as possible. Never remove or tamper with a 3-prong grounding plug. Use an adapter if you have to. These are often referred to as suicide plugs in honor of the people who didn't use them correctly. Make certain that the green wire is securely attached to a good ground. Always inspect a power tool carefully before use for breaks or cracks in the case, power cord, and plug. Even a small crack can sometimes allow moisture to get in and defeat the insulating capability of a wire's covering. Do not use a damaged tool. Return it, point out the damage, and get a safe one. Periodically, a power tool should be tested to determine that its insulation and ground wire are functioning. Check the continuity of the ground between the case and the ground wire prong with an ohmmeter or continuity tester. If there are no breaks, you'll find zero resistance. Extension cords should be treated in the same way. Don't use a cord that is cut, frayed, broken, or spliced. They too should be checked periodically. Testing between the plugs on both ends of the cord should indicate no breaks in the ground wire. Be careful not to run a cord through an area where it can be damaged. And if you are repairing a cord, it is important to make sure the polarity stays correct. Any ground connections to machinery should remain tight and free of corrosion and should have no breaks. Vibrations can cause a hot wire to contact the casing and make the machine electrically live. In some situations, the risk of serious shock can be much greater than normal. If you are working in wet conditions or in an enclosed vessel or any place else that makes it easy for you to come into direct contact with ground, you should use one of these. It's called a ground fault circuit interrupter, or GFI for short. In fact, OSHA requires their use on most construction sites unless careful inspection and documentation of good ground circuits is performed regularly. Put in line between the power outlet and the tool you're using, the GFI will sense any current going to ground, current that could be passing through you. At a very low level, less than 6 milliamps, the device will trip, and it trips much faster than a standard breaker does, making sure that your exposure to any current is too short to kill you. Never enter an enclosed vessel with an electric power tool or a ventilation device without using a ground fault circuit interrupter. Inside that vessel, you will usually be sitting or standing on metal. And the same goes for portable lamps. You should either reduce a lamp's voltage to a safe level, like 12 volts, with a step-down isolation transformer, or you must plug it into a GFI. How would you like to fall, break the bulb, and have your body complete the circuit from the filament to the tank? Or get between the tank and a cut in the cord? Not me. Now, the last area we're going to cover is the dangers of fire or explosion that can result from an overload on a circuit or from an electrical arc. Fuses protect equipment, not people. If something happens in the circuit that creates a demand for current that is higher than the wiring can handle safely, say a motor freezes up or some wires short circuit, what you should get is a blown fuse and not a fire. An element inside the fuse melts and the current is interrupted. Now, when you are replacing a fuse, it is very important to replace it with one of the same current rating. Never put in a fuse that has a higher current rating than the one you're removing. If a circuit can handle 20 amps, and you put in a fuse that will allow, say, 30 amps to flow, you've defeated the whole purpose of the fuse, and you've created a situation that could very well lead to a fire. Whenever possible, de-energize the circuit ahead of the fuse. Test the fuse to be absolutely certain that there is no voltage present. And then, when you're sure, go ahead and remove it. If you must remove a fuse from a live circuit, do it carefully. Never pull a fuse when it is under a load condition. An arc or flash can occur easily, burning you or worse. You should use the proper size of insulated fuse puller, like this. There are fuse pullers made for any style or size of fuse you are replacing. Now let me point out one more thing about fuses that you may not realize. What happened? Well, the fuses that we deliberately put in the box had the same load carrying capacity as the ones we took out, but their current interrupting rating was lower. Two fuses can be exactly the same in all respects except their current interrupting rating. This 200 amp fuse, which belongs in this box, has a current interrupting rating of 200,000 amperes. But this one has a rating of only 100,000 amperes. If we mistakenly put it into the circuit and a ground fault occurs on the line, the box could indeed explode. The point is, be sure that the fuse you put in is exactly the same as the one you've removed, including its load current rating and its current interrupting rating. Breakers and disconnects are rated in the same way. So if you are replacing either of these, you should be equally careful to replace it with one that is rated exactly the same. Now let's look at some other trouble spots that aren't nearly so dramatic, but can be equally deadly. Portable extension cords are also rated for voltage and current carrying capacity. Make sure the one you are using is big enough for the job. If the load is more than the cord was designed to carry, it will heat up and could start a fire. It's happened many times. Again, let me warn you that damaged cords are invitations to disaster. If a piece of a conductor has been torn away, it's become a smaller wire at that point, and its current carrying capacity has been reduced. It could heat up dangerously. And whenever a conductor has been exposed or severed, the danger of an electrical arc exists. Make sure that all connections are tight. Loose connections usually heat up and can start fires. Now, in an explosive atmosphere, the dangers of overheated equipment or of arcing are a very serious matter. All it takes sometimes is a small spark to cause a catastrophe. So make sure your electrical equipment is in excellent condition. And remember, an atmosphere of fine dust, like ordinary flour in the air, can explode too. Be careful and use equipment like this explosion-proof lamp that was designed for use in areas where explosion is a danger. Okay, we've gone over a lot of information on this program, the most important aspects of electrical safety. But now that you are aware of the dangers that can exist around low voltage, I hope you have enough respect for it to find out about other things you might need to know. We couldn't cover everything, so please make sure you understand the safety rules in effect at your plant or facility and follow them to the letter. Now, what if you do have a mishap? I'm afraid we better cover that too. If an electrical fire does occur near you, make sure you use the right fire extinguisher. It should say clearly on the label that it is appropriate for use on an electrical fire, or it should say that it is designed for use on a Class C fire. And what if someone gets a serious shock and you're nearby? First, get the power switched off as quickly as you can Seconds can make a difference. If you cannot cut the power, then try to pull the person off the circuit, and be careful not to endanger yourself. Use a dry, insulating material when you do it. If you touch the victim, you could wind up electrocuted yourself. Send for medical help as soon as possible. And if you know how to do it, administer life-saving techniques. It's a good idea to know how to get a person's heart going again and start him breathing. The electrician we saw at the beginning of this program was lucky there was someone nearby who knew how to save him. It's worth finding out about from the Red Cross or from your safety office. I hope you never have to use these techniques on another person. Even more, I hope no one ever has to use them on you.